So right now when we're traversing through in our memory viewer, here I am looking at the first dimension of that two-dimensional array. When I press space, it takes me into that array, and notice it's all 0x CD, CD, CD. This is the magic number identifying unused heap space. I can see data here, but what if I want to go back? What if I wanted to implement some process where I could press backspace, which would somehow allow me to go back to the pointer that I was just at before this one? How many pointers would I need to remember that I could go back to? This is a pretty common problem in computer science where you need a list. There are data structures that we can implement to solve this problem. I'm going to show you guys how to make a data structure from scratch that does exactly that. First, I'm going to make what's called a managed array. Just as an educational exercise, I'll make this as a struct. Our managed array needs to be able to do a few things. It needs to be able to add values to a list and retrieve those values. We also want to know how many values are in the list, and we want to remove values from the list. So this is going to inform what kinds of functions I need to write when I'm implementing the code for this thing. So at its core, a managed array is some kind of pointer to data and some kind of value that keeps track of how many allocated elements there are of that data. And if I want to add elements to there, I'll need a function that looks something like void add const int a value, this const int ampersand a value, although the const should probably go here. And then retrieve would look like this, int get int const ampersand a index. How many values? Int, I'll just call it size. Return allocated elements. And then void remove int const ampersand a index. Size will not modify the state of my array at all. However, add will, get won't, but remove will. What I've done here is I've added a bit of const completeness to these functions. Const ampersand means that the parameter that is passed into this function is not going to be modified during the get, and I'm going to pass it by reference. This gives C++ an option during its optimization step while it's compiling the code, and it allows it to reduce the weight of the stack frame of this function. And const, meaning that these promise not to modify data within the managed array. I've already written size. Size is a pretty straightforward function. It just returns how many elements our managed array is managing. I need to make a constructor, and in the constructor I'll initialize the data to 0 and the number of elements allocated also to 0. Add is probably not the function that we want to make here. I'm going to make a function called set size, and instead of a value I'll call it a size. In addition to a get function, I also want to make a set function that looks like this. Int const ampersand a value, and this will modify the contents of the array, so I'm not going to make it a const. It should be void set as well. This will set values. This will change the size of the list. So this is more in line with a managed array. I was getting a little bit confused earlier. A set size function would look like this. Int star new data equals new int a size. If there is already data that exists, then I want to copy all of the old data into the new array. For int I equals 0 while I is less than allocated elements plus I. New data I equals data I. I actually need to make this and I is less than a size, because if a size is smaller than allocated elements, I don't want it going out of bounds. Anyway, if there's data, this will copy all of the old data into the new array, and then I'll delete the old data, and then I'll set the data pointer to the new data, and set the allocated elements to a size. So this will change the size of the list. If I want to set data in that list, that's as easy as data a index equals a value. And if I want to get data from the list, that's as easy as return get a index data a index, and remove. You know what, I don't think we're going to need remove quite yet, so I'm going to go ahead and not do that function yet. There's a programming ideal called YAGNI, stands for you ain't gonna need it, and if you ain't gonna need it, you don't need to bother writing code for it. Let me change things around here a little bit. Data and allocated elements, as it turns out, are fully encapsulated by my managed array. The set size function modifies allocated elements, and it modifies data. When I want to get any elements out of this array, out of this managed array structure, I can use my get and set functions. This right here is what we call an accessor. Sorry, this wrong one. This is the accessor. This is a mutator, also called a setter, and this is also called a getter. This right here is also a getter, a accessor, because it returns data without modifying it. Getters are typically safe to make const because they shouldn't be modifying data. And all of this has to do with object-oriented programming. So one of the basic tenets of object-oriented programming is that you hide your data as much as you can. Public. We'll go ahead and make this a class instead. As a general rule, when you're doing object-oriented programming, you want to make as much information about your classes private, because that gives you more options as a programmer in the future to make your code better. For example, this is a terrible idea to make allocated elements public, because this has a huge role in the state of my program. If some user had access to modify allocated elements, it could break the way that set size works. It will clearly break the way size works. It will no longer serve its intended purpose of describing how many elements have been allocated by data. Similarly, if I move data out to be public, the user can just arbitrarily change where data is pointing. It's best to build your classes in such a way that other programmers, other users of your classes do not have to understand all the inner workings of how your classes actually work. So there's one more thing that I forgot here that I want to add really quick. Managed array destructor. If data, delete data. Alright, so now our managed array will clean up after itself as well. I think at this point this class is usable as a data structure for the purposes that I have in mind for it. So let me just test it really quick. Before I actually start implementing it in all of this code, I need to make sure that this class works. That's one of the benefits of doing things, of breaking things up into objects, is that you can test individual pieces. And once you test an individual piece and you can verify that it works exactly as it should, then everybody who needs that piece can work with it without having to worry about the complexity of that piece. I'm just going to visually spot check to make sure that it works. I'll make a managed array. I'll call it list, and I will set list size to 5, and I'll set all the elements in there. Size. List.set index I to 10 plus I. So it'll be 10, 11, 12, 13, 14. Then I'm going to print that data out. Printf %d, and if I is greater than 0, printf. Just so that I can have a nicer format. List.get I. So this is testing basically all of the functionality of my list. Creating the list with the constructor that just sets everything to 0. It's setting the size, which allocates data in the heap, a dynamic array, And if there's additional data in there, oh, that's another thing I want to test, if it'll resize correctly when I change the size. List.set size 7. Then we'll do this again, and I'll wait at the end. So it'll test to see if the setting size works. Get and set are tested here. Here it sets the data. Here it's getting the data while it's printing. And there's 2 for loops that do printing for me. And size is being used all over the place to verify how many times I need to iterate through these for loops. So let's run this and see if my class works. Ooh, no it doesn't. Let's run it in debug mode and see why. Break data index. Whoa, 784. Why is that happening? Let me take a look at the call stack. You can find the call stack by going to debug Windows call stack, and that'll bring it up. Call stack is here. So there. What is list size? Alright, that's 5. I is 784. How did I get... Oh, because I'm not actually... there's no condition in here. Alright, let's try this. Okay, let's try it. Yeah, looks like it's working correctly. Let me just verify that it's working correctly by looking at the memory. I'm going to pointer at the address of list. So here, 1, 2, 3, 4, these first 4 bytes are looking at the pointer to data. Right there, these 4. And then these next 4 are the allocated elements. If I scroll over here, 1, 2, 3, 4, 10, sorry, 7. A is 7, my bad. It's the alarm. The reason I jumped to 10 is because in hexadecimal, A is 10. Anyway, 7, which is the alarm, is the value here in these 4 bytes, which is allocated elements. That's what we would expect, because right here, we set the size to 7. So let me go into this array, space, and here we can see all of those elements. 10, 1, 2, 3, 4, 11, 12, 13, 14, and then 2 elements of undefined value. CD, 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 meaning undefined heap space. And pressing space there killed it. Okay.